Today we're going to take a look at inverse functions. Okay, we're going to start with some basics. So let's just look at basic inverse functions. We're not looking at trig yet. We're going to look at inverse trig later, but right now we're just looking at basic inverse functions. Okay, just a couple of things. You may recall that with inverse functions, the x's and y's are switched. In fact, that's actually how you find an inverse function. You switch the x's and y's and solve for the new y. We're not actually going to be finding an inverse function. We are interested in how to find the derivative of an inverse function at a specific point. And in order to do that, I'm going to show you exactly how to set that up. This is one of those things where you kind of have to have an intuitive understanding of what inverse functions are, in that remember that x's and y's are switched. So if it's an x coordinate for the function, it's a y coordinate for the inverse, and vice versa. And if we're trying to find a derivative of an inverse at a specific value, we kind of have to do the reverse with the regular function. We have to find where that function is equal to that y value in order to switch those coordinates. So let's just make sure to get this rule down. Suppose, okay, f negative 1 of x, this is the inverse function of x. We should have seen that before. Okay, and the point AB is a point on f of x. Okay, remember they're switched, so the point B comma A would be the point on the inverse function. Then the derivative of the inverse at B is equal to 1 over f prime of A. Okay, remember the x and y coordinates are switched. So if we're talking about B is a x coordinate for the inverse, that's the y coordinate of the original function f of x. Okay, this is definitely one of those things where when you first look at the problem, it just doesn't make a lot of sense, or as far as the actual rule. But once you start working through some problems, you kind of get a process down and it becomes a lot easier. So let's take a look at some examples. Okay, let's say that we have f of x equals x cubed minus 1, and we want to find the derivative of the inverse at 26. Okay, now we said the x coordinates of the inverse are the y coordinates of the original. So this is an x coordinate, 26 is an x coordinate in the inverse. So we need to see where f of x would be equal to 26. So where does it have that as a y coordinate? So the first thing we always want to do is take the original function and set it equal to that value. It's an x for the inverse, but it's a y for the original. So if we add 1, x cubed is 27, so x, has to be 3. Okay, so now we know the x coordinate. Okay, remember the rule we just said. Okay, if this is the b, okay, then this is going to be equal to 1 over f prime of the a, the x coordinate in the f, which is 3. So we have to find f prime of 3. Okay, f prime of x, the derivative would be 3x squared. Okay, f prime of 3 is going to be 3 times 3 squared, which ends up being 27. Now, that's not always the case. It just worked out for this one example that you're going to get that same number. So 1 over 27 is the derivative of the inverse at 26. Okay. Again, it becomes more like a process. You look at what's the x coordinate of the inverse. Okay, I'm going to set my function equal to that and figure out what x coordinate would have that y value. okay, because again, they are reversed when we're talking about inverse functions. Okay, let's try another one. Let's say we have the function 2x to the fourth plus x minus 1, and we want the derivative of the inverse at 2. Okay, so we want the derivative of the inverse at 2. Okay, 2 is the x-coordinate of the inverse, which means it's the y-coordinate of the original. So we want to set 2x to the fourth plus x minus 1 equal to 2. Now, I will tell you guys, this is definitely one that would be calculator inactive. Okay, and almost always these inverse function problems are calculator inactive. If you take a look, you might say, well, that's really difficult because I have an x to the fourth and I have an x, so how am I going to solve that? But usually they're whole numbers and they're easily calculated. Usually they're positive or negative integers that are close to 0. Okay, so if you start to run through some possible numbers, think about 0 is not going to work because that would give you -1. Okay, what about 1? 2 plus 1 minus 1, that's going to keep us 2, so x equals 1. Okay, again, because these are most of the time calculator inactive, they should be pretty easy to find the value that you're looking for. It should be relatively easy to figure that out. Okay, they're usually not going to give you one that's super difficult. Okay, usually it's 1, 2, 3, 0, -1, -2, -3. Somewhere in there in that range is usually what the value is that would make this work if it's calculator inactive. All right, so let's get back to where we were. We have the coordinates, okay? The x coordinate for the inverse is 2. Remember, that's the y coordinate of the original. That's why we set this function equal to 2. And we solve for the x value in the original function, which is 1. So we now know that this is going to be equal to 1 over f prime of 1. Okay, so we have to find f prime and plug in 1. F prime of x would be 8x cubed plus 1. F prime of 1 would be 8 plus 1 would be 9. So the derivative of the inverse at 2 would be 1 over 9. Okay, guys, another thing that people struggle with these is a lot of times they will try to take the negative reciprocal. Okay, that's a perpendicular slope. Okay, that's a perpendicular slope. That's not the inverse slope. So make sure that you just flip it. All right, let's try one more and then we'll take a look at inverse trig. Let's take a look maybe let's do a trig one. Okay, not inverse trig necessarily, but just a trig function. Let's say we have f of x equals tangent of x from 0 to pi over 2. And let's say we want the derivative of the inverse at 1. Okay, so remember, first thing we do is set the original function equal to this value. The x-coordinate in the inverse is 1, so that's the y-coordinate in the original. So we're going to set tangent of x equal to 1. Now notice we're on the interval 0 to pi over 2. So tangent is equal to 1 at pi over 4. Now we know that the derivative of the inverse at 1 is equal to 1 over f prime of pi over 4. So let's find that value. F prime of x is secant squared of x. If we try to plug in pi over 4, we would have secant squared of pi over 4. Secant of pi over 4 is square root of 2. Square root of 2 squared is going to give us 2. So now we know this inverse function at 1 is equal to 1/2. Okay? All right, let's take a look at some inverse trig. Okay, some inverse trig derivative rules. Just a couple of reminders. Make sure you keep in mind the range of values for your inverse trig functions. Arc sine is from negative pi over 2 to pi over 2, including those endpoints. Arc cosine is from 0 to pi, including those endpoints. And arc tangent is from negative pi over 2 to pi over 2, not including those endpoints, again, because there are asymptotes there. Okay. with your original tangent function. So also just a quick reminder of what things mean. If you see arc sine of 1/2, that's the sine inverse of 1/2. That's saying where is the sine equal to 1/2? And of course, that's at pi over 6. Okay. Notice pi over 6 is in between our range of values from negative pi over 2 to pi over 2. Okay. This becomes important when we are evaluating. If we are taking derivatives, maybe we're finding the slope of a tangent line. So we have to make sure that we still know our trig values, and we have to keep them within that range of values as well. Okay. Next thing, just a little reminder there, but next thing is actually look at the derivative functions for inverse trig. The first that we're going to talk about is the derivative of arc sine of u, okay, where u is some function of x. The derivative of that is u prime divided by the square root of 1 minus u squared. The derivative of arc cosine of u is negative u prime over square root of 1 minus u squared. Notice that one looks exactly like arc sine's derivative, except it is negative. That's a lot of times the way people remember that. It's exactly like arc sine, except it's a negative on top. Okay. Otherwise, it looks the same. Derivative of arc tangent of u, and again, u is some function of x. Derivative of arc tangent of u is u prime over 1 plus u squared. Okay, guys, I will tell you that arc sine and arc tangent are your most frequently used functions. Okay, we don't even look at the other three. We don't look at arc cosecant, arc secant, or arc cotangent. Okay, those are never used. These are the three that are most commonly seen, and of these three, arc sine and arc tangent are almost always the ones used. Sometimes, every once in a while, you see an arc cosine, but for the most part, it's arc sine and arc tangent. Okay, so let's take a look at a problem. Let's just start with a basic one and find a derivative. So let's say that we have f of x equals arc sine of 2x. Okay, we're going to start very basic. And we want to find f prime of x. We just want our simplified expression for f prime of x. Okay, remember we said derivative of arc sine of u is u prime over 1 square root of 1 minus u squared. So let's take that derivative. U prime, well, the u is 2x, so u prime would be 2 over square root of 1 minus u squared. So we need 2x all squared. So that's 2 over the square root of 1 minus 4x squared. We would leave our answer like this. No, you cannot take the square root of the bottom, so please don't try to do that. And our final expression would just be 2 over square root of 1 minus 4x squared. Okay. We could then use this in whatever way we needed to. We could use this to find where something's increasing or decreasing. We could use it to find the slope of a tangent line, just like we've used derivatives in the past. All right, let's try an arc tangent problem. So let's say we have f of x equals 3 arc tangent of x cubed. And again, let's just start with basic. Let's say we just want to find an expression for f prime of x. So if we take the derivative, 3 is a constant, so we're just going to multiply. Now let's take derivative of arc tangent of x cubed. The u is x cubed, so we start derivative rule here is u prime over 1 plus u squared. U prime would be 3x squared over 1 plus u squared, so 1 plus x cubed all squared. Okay, let's go ahead and simplify. 3 times 3x squared, guys, remember 3 is like 3 over 1, so we want to make sure that we only multiply the top by the 3. So that would give us 9x squared on the top. On the bottom, we have 1 plus, and then x cubed all squared would be x to the 6th. So that would be our derivative function. We could then use this to find slopes of tangent lines. We could also use it to find where functions are increasing or decreasing, anything that we normally would use it for. We could then take a second derivative if we needed to determine concavity of the original function as well. All right, let's try another one, and this time let's find a tangent line. Okay, so let's say that we want to find the equation of the line tangent to f of x equals 2 arctangent of x over 3 at the point where x equals square root of 3. Okay, so just like normal, we need to have the derivative so that we can plug in the x value to find the slope, and we need to plug the x value into the original so that we can find the y coordinate. Okay, so let's start. We're going to find, let's just go ahead and find derivative. Okay, so 2 is just a constant. Derivative of x over 3, remember x over 3 is like 1/3 x. So we've got 1/3 on the top. On the bottom, we have 1 plus u squared, so that's x over 3 all squared. So we have 2/3 over 1 plus x squared over 9. Now, we can actually leave our derivative like this because we're just going to plug in a value. But I'm going to go ahead and simplify it down just so we get some more practice with that. All right, so let's say we get a common denominator on the bottom. That would be 9. So we'd have 9 plus x squared over 9. Whoops, not 2. 9 plus x squared over 9. Flip and multiply by 9 over 9 plus x squared. And then notice 9 over 3 would cancel to give us 3 on the top. So we would end up with 2 times 3, which is 6 over 9 plus x squared. Okay, so that's our derivative function. And again, we didn't have to do that because we're just plugging in values, but I wanted us to practice a little bit more with simplifying down. I think sometimes that's where people make some careless mistakes, especially if it's just asking you for the derivative function. You may look at this and go, well, how would they get 6 over 9 plus x squared? Now you know. Okay, so again, just some extra practice simplifying down there. Okay, let's talk about the things we need. We have the derivative now. We need to plug the x coordinate into the original function to get the y coordinate. We need to plug the x coordinate into the derivative to get the slope. So let's plug into the original first. If we plug into the original, we have 2 arctangent of square root of 3 over 3. So that's saying where is tangent equal to the square root of 3 over 3, which happens at pi over 6. Remember that we are solving within the range of values, which is from negative pi over 2 to pi over 2 for arctangent. So 2 times pi over 6 becomes pi over 3 for our y coordinate. Now let's plug into the derivative to get the slope. So f prime of square root of 3 is 6 over 9 plus. If we square the square root of 3, we're going to get 3. So we have 6 over 12, which is 1/2. So now let's write out our equation of our tangent line. Y minus the y coordinates pi over 3 equals the slope, which is 1/2, times x minus the x coordinate, which is square root of 3. And this is definitely one where it's nice that we can leave this in point slope form, because notice we've got fractions, we've got square roots, we've got pi. So if we tried to combine that, it would get pretty ugly. And so we don't have to do that. We can leave it in point slope form. Okay. And if this was a multiple choice, they'd actually probably leave it in point slope form like this as well. So that's kind of nice about those types of questions. If it was free response, obviously you could leave it in point slope form as well. All right. I'm going to try one more. Okay, let's do one more. Same thing, we're going to find. Okay, I'm not going to write it all out. What I'm going to do is just write out the function. So let's say we want to find the derivative, or excuse me, find the equation of the line tangent of the function arc sine of x over 4 at the point where x equals, let's say, 2. Okay, so let's take a look at this one. And actually, I'm going to make this one -2. Let's call this -2, just to make it interesting. So we're going to find the slope of the tangent line and the y-coordinate so that we can plug in and write out our equation. We need to get the derivative. Okay, remember, derivative of arc sine is u prime, so 1/4 would be our u prime over square root of 1 minus u squared, x over 4 squared. Now, because we're plugging in, we could go ahead and plug in. We don't need the actual derivative simplified, but I'm going to go ahead and simplify it anyway, again, so we get a little bit more practice with that. So we have 1/4 over the square root of 1 minus x squared over 16. Get a common denominator. That's 1/4 over square root of 16 minus x squared all over 16. Take the square root on the bottom here. That would leave us with 1/4 over the square root of 16 minus x squared over 4. Flip and multiply. We're going to multiply by 4 over the square root of 16 minus x squared. Whew, barely fit it in. 4 over 4 is going to cancel, and our derivative ends up being 1 over the square root of 16 minus x squared. Okay, again, we didn't have to do that, but I wanted to go through and make sure we have a little bit more practice simplifying. So we need two things again. We need the y-coordinate and we need the slope. So let's plug into the original to get the y-coordinate. Plug in -2. If we plug in -2, arc sine of -2 over 4 is -1/2. So this is saying where is the slope, or where's the slope? Where is the sine equal to -1/2? Okay. Sine is +1/2 at pi over 6, so sine is going to be -1/2 at -pi over 6. Now, again, this is where a lot of people make mistakes because they don't remember their range of values. The range of values for arc sine is from -pi over 2 to pi over 2. So we had to pick something from that negative portion for this one since we had -1/2. Okay, so -pi over 6 is our y-coordinate. Now let's plug into our derivative to get our slope. 1 over the square root of 16 minus -2 squared is going to be 4. 1 over the square root of 12. Okay, we may want to simplify. That'd be 1 over, let's see, 2 squared to 3. Okay, you don't have to rationalize that. You can if you want to. You'd end up with what? Square root of 3 over 6. So you could if you want to. I'm not going to because I don't need to. Let's write our tangent line, y minus negative, so it becomes plus pi over 6 is our y-coordinate, equals the slope, 1 over 2 squared to 3, or square root of 3 over 6, however you want to write it, times x minus negative, so plus 2. And that would be the equation of our tangent line for this function at x equals -2. All right, guys. Hopefully you did pretty well with this. The big thing is you have to know your rules. So just make sure you memorize those rules. And most of the time, these are calculator inactive type questions. So they should be relatively easy to calculate. Again, because they are not allowing you to use a calculator. Almost every question I've seen with arc sine or arc tangent or with your inverse functions are usually on the calculator inactive portion of the exam. So just make sure you're good with those trig values. That's really important, especially keeping in mind those range of values because that's what most people mess up on. They forget about the range of values for arc sine and arc tangent.